Okay, to our new members and guests, I want to welcome y'all. We're delighted to have you join us this evening. Our members have many wonderful opportunities to share observing the beautiful night sky and to make new friends and lasting memories for themselves and families. Plus, there are also opportunities for public outreach to get others interested. Please feel free whenever you're out at our events to ask questions, offer suggestions, or even volunteer to help out at our events. And all new ideas are welcome, and we're glad you're here. Okay, upcoming events. Our members only observing nights will return to Friday evenings. Saturday nights will be our backup night. We are not planning public events until the pandemic subsides. Okay. Our next members night is Friday, June the 4th at the observatory at 8:15. Following that, our next members night is Friday, June 11th at the observatory, also at 8:15. And then for July, members night is Friday, July 2nd at the observatory at 8:30. And then following that, the next members night is Friday, July the 9th at the observatory at 8:30. All right.
I might mention that the backup nights, weather backup nights would be on Saturday. I didn't put that on there.
Yeah, the backup nights for June the 4th, it would be Saturday, June 5th. For June 11th, it would be Saturday, June 12th. For July, it would be Saturday, July 3rd. And for the 9th, it would be Saturday, July 10th.
Thank you.
Oh, you're welcome. Now, observing nights guidelines. Now that COVID restrictions are easing and many people are fully vaccinated, we are adjusting the guidelines for our members' nights. Masks will not be required when you are outside. However, when you are inside the classroom or viewing in our dome telescope, we request those who are not fully vaccinated to respect others' health by wearing a mask. This mask guideline does not apply to younger children. We will leave that to their parents' discretion. If you decide to join other members at their telescope, we would advise that you ask their permission. Our restroom and classroom are open. Please exercise proper hand washing and other common health hygiene practices. Observing these guidelines will help us continue to enjoy our hobby while keeping ourselves and others safe. Okay.
Okay, we're going to turn this over to Mr. Skip again. And I'm not going to steal his, but there's some images of our new Ash Dome project. So I've got to unshare, don't I? Sorry.
Carry on. All right.
All right, you ready to share, Skip?
Yes, I am, I think. Let's see, there it is right there, here. Okay, we just to reiterate something that we've been talking about for several months now. The club had donated a 12-foot 6-inch diameter commercially built observatory dome made by the Ash Manufacturing Company, and they go by the name of Ash Domes. This one was built in 1966 and was originally bought by my father for his, he had it built on his horse farm in Alabama. I used it a lot when I was a teenager, and not so much once I moved off to college in 1970, just very, very sporadically after that. But Dad continued to use it a lot up until he had to sell the property for health reasons in 1996. So in 1996, I got in touch with Ash, and they were still in business, and asked them if they had a recommendation for taking it down, and they sent instruction. They said, start at the back and work towards the front. And so he and a couple of his hands took it apart, put it in storage. And then after he died in 2000, I moved it to Tulsa. was trying half-heartedly to find a home for it, offered it to the club, but we had nowhere to put it. Tried to sell it and didn't get much interest, and it was taking up space in my basement. So it got offered to a coworker who said he might be interested in it. So I said, you got right of first refusal if you will store it in your house. So he did, and it was there until about 2 months ago. And after we acquired the additional land, we have space to put it now. So I contacted him. He still had it. About 8 years ago, with permission, I had actually been approached by the University of Central Oklahoma to put it on their, donate it to them so they could use it at their Selman labs out by Woodward. And I gave it to them, took a tax deduction. And then the oil crash came and they didn't have any funding, so they never claimed it. So when it still existed, we had a place to put it. I got in touch with them and said, can you give it to another charity? And they said, sure. And so they turned it over to us. We went and got it. And it's in James Taggart's workshop now. And here are James and Don putting the, and we were going through it because it's been in storage for about 25 years, actually going on, 25. We wanted to make sure the parts were still all present and in good enough shape that they still work. So we're putting it together inside the workshop just to check it out, get familiar with putting it together. And after we're convinced that it works, we're going to take it apart again, clean some rust off of it, do a little bit of maintenance and prep, and then put it in storage while we design a building and try to find some money to build. So here's James with Don supervising, putting some of the rollers that the dome rotates on top of a couple of rings that are spliced together, some rings that are spliced together that form a 12-foot, 2-inch diameter circle that fits on top of the dome wall, cylinder, or whatever fitting you have on top of an otherwise shaped building. After all of the roller clips are in place, we built these little temporary brick piers. There's 20 of them. There's 20 rollers, and there's supposed to be 20 holes in the circumference of the ring, but I think it's something like 18 that where it gets bolted down. And one of the instructions says to make sure that this ring is perfectly flat and level. So this little slick little laser level here is the cat's meow for that. But unfortunately, we discovered that this wasn't a very stable arrangement. When you push on the dome, it would shift and we would lose the level, and then things would not work so well. They were right. And another problem we found was when it was being taken apart, you had a couple of men on top of ladders working. This piece is probably 13 feet long and weighs, I don't know, 50 pounds. And it's on rollers. So anyway, when they were taking it apart, it looks like it got bent a little bit. And that's one of the things that we're cautioned against, but that was deep in the past. So Ken Weichel, who is our sheet metal guru, applied some of his magic to it. Here's a couple of the rollers that the dome rotates on. These are heavy duty garage door rollers. And then he took his calibrated hammer and finished that up, and it actually improved it enough so that it actually did roll. It was binding at those splices the first time we tried it. So he did some magic on it, and it does work now. It's still not perfect, but it's very close. Next step after assembling that was to begin to put the skin on the dome. And so here are we have the first 3 panels. These panels slide together. That's each one has a center rib and then a rib that slides and mates with the adjacent panel. And then there we are, kind of tweaking the ends a little bit just so it makes it a little bit easier to put together. And also we found that dishwashing detergent makes an excellent lubricant to help these things slide together a lot better. You don't have to worry about it staining and making a mess because it'll eventually just wash away. And there was the dome as it existed after the first weekend, probably 6 or 7 hours of work on Saturday, another 3 hours of work on Sunday, and we were at this point. And I'm going to unshare this screen and share a different one. There we go, share. And here is Ken rotating. Go. Oops. All right, I'm going to unshare that, and I'm going to change reels. I should have this queued up. Oh well.
While he's doing that, the final version as it sits today is behind James, is in his picture there.
So here's one of the things we found was that the dome would slide around on those brick piles. And so we changed to, we borrowed some concrete blocks that are stored behind the observatory and replaced the bricks with those, and that helped. But still, if you pushed on this thing, and it has a fair amount, it's fairly heavy, and it takes a little bit of a shove to get it started, and it would shift some. So one improvement we made was we used ratchet straps to secure it to the building frame and some really heavy equipment. And that makes all the difference in the world. Now it's pretty solid, and we're not constantly having to re-level it. So here's James. Now this is the track that the shutter runs on up and over the top of the dome. And it had about 30 years of Alabama dusty rain, crud built up in it, a little bit of grease. We was cleaning that out just to get ahead of the game. And then here's the dome with the two side rails, the shutters roll on attached. And then a view up through the top. It's got an interior trim piece here that kind of dresses out the inside. Down at the other side here, this is the left side, and that's the right. At the left side here, you can see is that they didn't waste any effort or money cleaning that cut up. It looks like it was cut with a sawzall, and this started out life as a silo dome. You cut it with sawzall, and it's got a ragged edge and as sharp as a knife, and so you have to be careful working around it. But that's all covered up with the trim. Once we finally got that all the trim pieces in place, that's what it looks like from the interior looking straight up. This hole here, a big gear sticks through that and engages a rack, a gear that runs along the inside of the shutter to drive it up and over. And this particular dome has the feature, I'll call it a feature, that it's manually operated. And when it was originally delivered, it was on 7-foot tall walls, and the dome itself is a hemisphere 12 and a half feet in diameter. So there's another 6 feet above that. It came with a 7-foot long awning crank that you would hook onto a ring to drive the shutter open. It took a lot of cranking, but it wasn't terribly hard work. And so that is basically where we stand now. And as Don pointed out, you can see the dome in its current state. You don't have the shutter on it yet. That's going to be next, and that'll probably be a week and a half or so. We're going to skip this weekend and then resume after Memorial Day weekend. So point out to you behind you, James, and you're muted.
Beautiful.
And also, if if we're working on it during the weekend and some of you guys want to come out and see it, come on by. We can get you directions.
Oh yeah. Might even put you to work.
It'll still be set up for the weekend of the that first members night, probably the second. I'm pretty sure it'll be for the second one too in early June. So maybe stop by on the way. It's only about 5 miles from the observatory.
Yeah.
So
If you're coming from Tulsa, you can't not pass our house.
so come by and see it. It's really pretty cool.
Maybe we could even, at the members meeting night, we could have this telescope that we're planning to put in it.
Yeah, that's currently set up in my living room right now. I put it through its paces, and I'm planning on bringing it out to one of those. We have a donated 6-inch refractor that on an Atlas mount that is the intent to be the starter in that. Nice thing about the Atlas is we can substitute any telescope that has a dovetail basically for that one as we see fit. If we are clever with how we do the pier, we can probably swap the mount out, and it's the sky's the limit.
Well, that's a good closing line there, Skip. Thank you. I've got a little short thing to share, and then we'll get into our main program. If I can bring this, I think this is the one I was on. Whoops, that's not gonna work. I got to unshare because I forgot to click the 2 little magic buttons. Nope, they're clicked. Sorry. So there's our report on our ash dome and all our participants. And I want to tell you about something that's coming up in Broken Arrow. I don't know how to get that. Are you seeing my little sheriff bar? Or are you seeing the screen? Anyway, Broken Arrow is working on a project to bring a 1/10 billionth scale solar system walkway to Broken Arrow campuses. Back in the late 90s, we had a astrophysicist named Jeff Goldstein that visited our school system a couple of times, a very charismatic, inspirational type speaker, visionary. And while he was here, I know what 1 month he was here was November of '99 because we had a transit of Mercury. But he envisioned this 1/10 billionth scale idea, that the distances between the planets and the size of the planets would be the same. And he even gave me a paper model of it that I used with my classroom students. But basically, it's going to start at an elementary school just east of what we call Lynn Lane here in Broken Arrow, a little bit east of Bass Pro, about a mile, and extend for nearly 2,000 feet toward the high school. The scale is 1 AU is 15 meters. So it's with the beginning and ending part of the walkway, it's a little bit less than 2,000 feet. And the scale of the objects and the scale of the planets is the same. So that golden disc there is about the size of a decent sized grapefruit. That represents the sun. It's at a height where people can reach up and touch it. There's all sorts of information there about the sun. I understand that the new model, this is one of the original ones, but the new ones even kind of have one of those things you can scan with your phone, a QR code or whatever they call them. So you can experience firsthand what the scale of the solar system is. And since it was my job to lay this thing out, I probably covered 12 miles back and forth, getting it all laid out. They were real picky. They wanted it right down within a centimeter or two. So anyway, the stanchions, as they call them, are aluminum, anodized aluminum. They're just under 8 feet tall. They've got a nice informational display. There's some raised lettering on it for people who are vision impaired. It's not Braille, but and they're supposedly going to have these new QR scannable codes that can bring up audible stuff. This one is one that's in Corpus Christi, and you can see how they're kind of strung out down the boardwalk there. We're currently in the fundraising mode. We need $50,000. We've got 13 committed now. We have sponsors for Jupiter and Mars. And so we're seeking business sponsors or individuals who would like to donate to the project. If you want to know more about it, there's not enough room here to give you all the information. But I can do that if you want to contact me. There's my email. But I think it's going to be a really neat thing. It's when we were talking about it, they were inviting us to maybe set up there along the walkway. It's a big open lawn about a mile east of Bass Pro. So it's not as bright as the Bass Pro area. So we might be able to do some of our events there too. Really nice idea. School children, families, everything like that. The one there on the screen there with the children is the one that's on the National Mall. So if anybody has questions about that, they can contact me. But that's not our program for tonight. Is everybody hearing me?
Yes, sir.
Okay, I wasn't sure if you were hearing me. Our program for tonight is about the Artemis mission to the moon and looking for resources on the moon. The plan is both ourselves, Europeans, the Russians, the Chinese, Russia, China, United States, Israel, several countries of India have sent missions to the moon of various kinds. But the logical step, which I thought was going to happen right after we went to the moon in the 70s, is to establish a moon base, a way to live on the moon, and as a stepping stone to learning how to move out into the rest of the solar system. The moon is 3.5 days away versus Mars, which is a 2-year journey back and forth. So the speaker tonight is Dr. Casey Honniball, and she's a lunar, as she calls herself, a lunatic scientist. And her team has been looking for the most precious molecule in the universe as far as life concerned, and that would be water. So I'm going to bring up the YouTube. There's the address if you want to look at it later. When this is a recording of one of our Night Sky Network programs, so they have a Q&A at the end, but we will not be able to participate in that. So you can listen though. So oops. And where did it go? I thought I had it up here. Let's see if I can bring it back up. That's not it. Maybe this has it. I can't get rid of that thing at the top. Anybody know how to get rid of that bar?
John, are you, is that screen full screen or just a window?
Well, there's a link at the top.
Yeah, so John, I think you have the application selected, not your screen.
Okay, that's not what I wanted to do. little patience, I'll figure it out here. Nope.
Is it the Artemis 1 NASA plans to travel beyond the moon, the YouTube video?
Yep, here it comes. Hang on.
Okay.
Are you seeing it come up?
No, not yet. We just see you right now.
You just see me? Okay, we'll go to Zoom.
You go back to that link. I can.
Share.
Okay, there you go.
There it is. Okay.
Okay. Here we go. Yeah, we got you now.
Got it?
We could see somebody there with seagulls in the background.
Yeah, that's the Night Sky Network guy. Okay, I'm sorry. Amateur hour here.
Enter that into the Q&A window. Keep your chatting with.
Are you able to hear him?
Yeah.
Yes.
Okay.
Barely. But my hearing's not that great anymore.
each other in the chat and all the questions into the Q&A. That will definitely help us keep track of your questions and let us know whether or not we've answered them or not. So again, welcome to the May webinar of the NASA Night Sky Network. This month, we welcome Dr. Casey Honniball to our webinar. Dr. Honniball is a lunatic, a lunar scientist, research fellow in the NASA postdoctoral program at NASA's Goddard Space Flight Center. Her current research focuses on characterizing water on the moon and testing field portable instruments for use by astronauts during their EVAs on planetary services. Her PhD is in Earth and Planetary Science from the University of Hawaii, and she and her team announced the direct detection of water molecules on a sunlit portion of the moon using the airborne telescope SOFIA. Since then, she's made numerous media and outreach appearances to talk about lunar water, including joining us here. So please welcome Dr. Casey Honniball.
Hi, everybody. All right, let me get my screen sharing. Okay, let me know if this is not sharing for you guys.
Looks good for me.
All right, so hi, everybody. Thank you so much for allowing me to talk to you today. So as he said, my name is Casey Honniball, and I'm a NASA postdoctoral fellow at NASA Goddard Space Flight Center in Greenbelt, Maryland. Today, I would like to talk to you about the NASA Artemis program to explore the moon like never before, and how we're preparing for a sustainable lunar presence using the moon's most important resource, water. So Artemis is the twin sister of Apollo and goddess of the moon in Greek mythology. Through the NASA Artemis program, NASA is preparing to land the first woman and the first person of color on the moon using innovative technologies to explore the moon and the lunar surface more than ever before. We will work with academic, commercial, and international partners to establish sustainable presence on the lunar surface. And we will use what we learn on the moon to explore even farther and take the next giant leap of sending astronauts to Mars. To embark on the goals of Artemis. Everything okay?
Looks great.
We're good. We're good.
Okay. So to embark on the goals of Artemis, we need a system to get our astronauts to the moon. They will launch on the world's most powerful rocket, the Space Launch System. They'll ride in the Orion capsule to the lunar outpost called the Gateway that will be in orbit around the moon. From the Gateway, astronauts will descend to the lunar surface via the recently selected SpaceX Human Landing System. Through this system, we will have access to all locations around the moon. America will be again a leader in space exploration. The Artemis program will advance us from mapping the moon to establishing a sustainable presence on the lunar surface. From studying the moon from samples and instruments to exploring the surface in person. And from learning about Mars to answering fundamental questions about the history of water on both the moon and on the Martian planet. So the Artemis mission is made up of 2 phases. Phase 1 is to achieve human landing on the surface of the moon, and phase 2 is to build a sustainable presence on the surface of the moon. So I'll focus on phase 1 here, and that's the current mission phase. So during this phase, we are preparing to send our astronauts back to the moon. We will first send Artemis 1 into orbit around the moon to return safely home. This is an uncrewed integrated flight test of NASA's Orion spacecraft and the Space Launch System. This mission will last anywhere between 26 to 42 days and is expected to launch in November of this year. Artemis 2 will be the first crewed mission of 4 astronauts with the objective of confirming all spacecraft systems operate as designed with crew aboard and in the actual environment of deep space. During all of this, the Gateway lunar outpost will be assembled. First, the solar electronic propulsion system will be sent to orbit the moon. And then the first pressurized module will be installed. And then lastly, the human landing system will be delivered to the Gateway to prepare for Artemis 3. Artemis 3 is the main headliner. It will send 4 astronauts aboard the Orion spacecraft and head to the Gateway outpost. Once there, 2 astronauts will stay aboard the Gateway, while the other 2 head down to the lunar surface on the human landing system. Once on the surface, the astronauts will spend a week on the surface conducting science experiments and setting up infrastructure that will begin the next phase of building a sustainable presence on the surface of the moon. So many people have said, we've been to the moon, why should we go back? Or why not go straight for Mars? The answer to this is actually very simple. The moon is our closest celestial neighbor, and it is just a 3-day trip away, compared to the 8 months it takes to get to Mars. By going to the moon, we can develop new methods that we need to survive on Mars while being within reach if something were to go wrong. On Mars, if something goes wrong, you're on your own. It's better to test our habitats, technologies, and procedures on the moon before sending astronauts to Mars. With the ultimate goal of expanding humanity's reach into the solar system, the moon is a critical stop for turning science fiction into reality. While on the moon, we can test new technologies for life support systems or construction of habitats in low gravity environments and extreme conditions. All of the work we do on the moon prepares us to make the journey to Mars. The return of American astronauts to the moon will place America in a leadership role for space exploration similar to the Apollo era. It will inspire the next generation and encourage careers in science, technology, engineering, and mathematics. The Artemis program will feed back into our daily lives, just like Apollo did, with new technology being developed and adapted for our everyday use in our everyday lives. To fulfill humanity's basic desire to explore, the moon is the next frontier. So let's go over a little bit what we've learned about the moon and what we currently know. So prior to Apollo missions, little was actually known about the moon. Here are just a few things that Apollo taught us. Originally, we thought the moon was only hundreds of million years old. But once Apollo returned samples, we learned that the moon is actually 4.5 billion years old. This is similar in age to the Earth. We expected the moon to be made of unmelted, primitive meteoritic material that formed by accretion and has always been cold. But what we found from Apollo samples is that the moon is actually made up of rocks that can only form inside of magma. The theory that all planets form cold was dismissed, and the moon had to be molten when it formed. And long ago, early astronomers believed that the dark patches on the moon, known as Maria, were once dried up oceans. However, most lunar geologists actually knew that the Maria were lava beds, but they expected the moon to be very dry, but they weren't sure how dry. Well, it turns out that the moon isn't entirely dry, and water can exist on the surface. And the Maria were never oceans of water, but they were actually oceans of lava. So now I'm going to play a video for you about the evolution of the moon, and it's going to give you a glimpse of how the moon formed to what we see today.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye, as a permanent record of its own history, and a glimpse of how craters may have formed here on Earth.
Okay, so let's continue this little tour of the moon. We always see the near side of the moon, and that's because the spin of the moon is the same length and time that it takes the moon to orbit the Earth. The near side has two distinct features, the light areas of the highland and the dark areas of the mare. These two features represent rocks of different composition and age. They provide evidence into how the early crust of the moon formed from the giant ball of magma. Craters that formed expose material from deep inside the moon and preserve the impact history of the moon and other bodies like the Earth where the impact history has been erased. The far side of the moon, however, many people have never even seen an image of. You might think it should look the same as the near side. But instead what we see is that the far side of the moon looks nothing like the near side, with only 1% of the far side being covered in the dark mare patches. The near side has higher concentration of radioactive elements that decay and produce heat inside the moon, making it easier to produce magma that can erupt into from lava flows. The near side also has a thinner crust from many large impacts, also making volcanic eruptions easier. On the far side, there are not many large impact basins, and the crust is a lot thicker, making the volcanic eruptions a lot harder on the far side, and so the appearance of the dark mare patches is rare. So even though we've been studying the moon extensively for decades now, there's still many things we don't know about the moon. So what can we still learn about the moon? So I'm going to play one more video for you, and this one is actually my favorite. It's going to walk through just a handful of things that we still need to learn about the moon.
The moon is our nearest neighbor, our nightlight. It's also our memory. While wind, water, and molten rock erase Earth's deep history, the moon remembers everything that has happened in the last 4.5 billion years. The impact that formed the Oriental Basin provides a window to understanding how similar large events on other planets and moons have shaped their landscapes. The discovery of water on the sunlit surface of Clavius crater not only unlocks new possibilities for future lunar exploration, but also our understanding of where the ingredients of life could exist in our vast universe. The steep trenches and cracked surface of Komarov crater on the far side tell a story of the ancient volcanic activity from the moon's interior, revealing the history of geologic forces carving the lunar terrain through time. Traversing the landscape, we can see a beautiful tapestry of ridges, valleys, and mountains, best encapsulated by the view of Tycho crater. The summit of its central peak stands nearly 3 miles above the crater floor, a visual metaphor for the steep challenges but exciting rewards that await us on the moon and beyond. And on the lunar horizon, the most consequential view of all, our home. To study the moon is to study ourselves, our past, our present, and our future. Each new discovery bringing us from darkness into light. The gravitational forces between Earth and Moon make our very existence possible, creating one of the most special relationships throughout time and space.
So this video only touches on a handful of things that we can still learn about the moon, but there is so much more we still don't know. By returning to the moon, we can learn more about planetary processes, like how volcanism shaped the moon we see today. We can find the origin of polar volatiles like water ice, study the history of impacts on the moon that tells us about Earth's bombardment history, which has largely been erased by weathering, erosion, and plate tectonics. We can look at the behavior of the sun over the past 4.5 billion years ago. We can set up a radio telescope on the far side of the moon, away from all the noise that confused radio signals here on Earth. We can test how physical and biological systems behave in low gravity and vacuum environments. And lastly, we can study the risks of space exploration and work to mitigate them for safer exploration to planets like Mars. Another unique thing about the moon is that it provides access to resources. The image in the back is a geologic map of the moon's near and far side. The colors represent different minerals. All of the minerals can be extracted for resources. The list in the middle are just some of the resources the moon has to offer. These can be used for a variety of purposes, such as life support, building materials, fuel, or power. The Artemis mission relies on research we do to understand the processes occurring on the moon and the available resources. So the moon is a cornerstone for solar system science. For the Artemis program to be successful and sustainable, we need to understand everything the moon has to offer. Of particular interest are volatiles on the moon, such as water, which is likely going to be the moon's most important resource. But before we can prepare to use any water on the moon, we must first understand its life cycle, sources, deposits, and losses. So why is water so important? For humans to survive anywhere, we need water to drink. But water can also be broken down to create breathable oxygen, rocket fuel. If we find that the moon has large enough quantities of water that we can use, then when we send astronauts to the moon, they won't need to bring all the water and fuel they need for their stay. Take camping, for example. If you go backpacking in a dry, remote location, you need to bring everything you need to survive. Imagine having to carry 3 gallons of water for a 5-day camping trip. That would be pretty heavy during your journey to the camping site. Now imagine instead that you're camping next to a river. Instead of bringing all the water you need, you just need the correct materials and supplies to make the river water safe to drink. This would be much less weight to carry. For space exploration, launching water is expensive, costing roughly $25,000 per gallon of water. So if we can use water from the moon, we can create a more economical and sustainable presence on the surface and journey farther out into the space. So, what do we know about water on the moon? Let's go back in time to 1952, 17 years before Apollo 11 would land on the moon. It was theorized that the poles of the moon, inside regions of permanent shadow, there would be water in the form of ice. This video here is zooming in on the south pole of the moon, showing where sunlight shines. If you pay close attention, you'll see some areas never receive any sunlight. These are the permanently shadowed regions that were theorized to store water ice. Now let's watch this video one more time. So this time you're going to notice that when we zoom in to the South Pole, you're going to notice there's these blue areas, and these are all of the permanently shadowed regions. You might notice there's a lot more of these regions than you saw in the first video. So it's these areas in blue that scientists in 1952 thought might be trapping and storing water ice. However, once Apollo missions returned samples from the moon, researchers found no evidence of water of any kind or form. This led everybody to believe that the moon is a very dry place. But as the years passed, new and improved technology emerged. In 2008, researchers decided to reanalyze special Apollo samples. During Apollo 15 and 17, some samples that were brought back contained black, green, and orange glass beads. This image shows an Apollo 17 sampling site where you can sort of see that the regolith here appears to be orange. Now taking a closer look at this, the orange soil really stands out against the gray regolith or soil of the moon. The glass beads that were found during Apollo 17 were orange and black. And these beads are special because they formed during a volcanic eruption on the moon. These beads were reanalyzed with the new technology, and researchers found high water contents inside the beads. Now, what they actually measured was hydrogen, but the amount of hydrogen measured can be converted to the amount of water present if all of that hydrogen was in the form of water. The next year, in 2009, 3 spacecraft reported the detection of a hydration feature on the surface of the moon, something that no one actually expected. These images here were taken by the Deep Impact spacecraft that did a flyby of the moon. This last image here on the right shows how much hydration Deep Impact measured, with the reds and yellows representing high amounts of hydration. The 3 spacecraft all detected what we refer to as the 3-micron hydration band. 3 microns is an infrared wavelength just beyond what our eyes can see. This plot on the left is showing an example of this 3-micron hydration band similar to what the spacecraft would have observed. This band is created by molecules that have both a hydrogen and an oxygen atom present. This means that the 3-micron hydration band is attributed to the presence of either hydroxyl, which is OH, water, H2O, or both. So for example, if drain cleaner's active ingredient is hydroxyl, and if water and drain cleaner were on the moon, we couldn't distinguish between the two at 3 microns. In the same month that the 3-micron hydration band was reported, a man-made projectile struck a permanently shadowed region inside Cabeus crater located at the lunar South Pole. The goal of this L-Cross mission was to eject debris, dust, and vapor, which may contain highly volatile substances like hydrogen gas, ammonia, methane, and water. By observing the ejecta, L-Cross detected water vapor and water ice. This detection is the first evidence of water on the moon in permanently shadowed regions, like had been predicted in 1952. Following the L-Cross mission, water on the moon was mainly studied using data obtained from the Moon Mineralogy Mapper on board the Chandrayaan-1 spacecraft that collected global observations of the moon in the near infrared, including that 3-micron hydration band. This map shows high hydration in blue, mainly at high lunar latitudes near the poles. Using the same data set in 2018, MCube researchers were able to make a map of water ice at the lunar poles. This image is of the South Pole, and water ice is found at all of those locations in teal. All the water ice detected by MCube resides within these permanently shadowed regions. Now, up until last year, all evidence for the actual water molecule on the surface of the moon was in the form of water ice in these permanently shadowed regions. But outside these cold, dark places, water on the sunlit moon had never been detected. And scientists were still trying to figure out if this 3-micron hydration band was even partly due to water. So let's go over why there's such confusion about the 3-micron hydration band. The 3-micron signature of hydration is created when a hydrogen and an oxygen atom are bound together. The molecules containing hydrogen and oxygen stretch symmetrically and asymmetrically, like shown by these little molecules here. This motion of the molecule shows up as the 3-micron hydration band, like shown in this plot. The 3-micron signature for hydroxyl is similar to the 3-micron signature of water. Further complicating things is that hydroxyl binds to lunar material, allowing it to mimic water signature almost exactly. As of right now, we don't know how to separate the two at 3 microns. So with the 3-micron band on the sunlit moon, it could be either hydroxyl or water. This is where part of my work on lunar water comes in. Previously, all the detections of water and hydration was done in the near infrared, where water and hydroxyl can be confused. This got me and my graduate advisor wondering why we're not looking for a different water-only signature to determine if water can survive outside of these permanently shadowed regions, but on the sunlit surface of the moon. So we developed a new method to look for water on the moon, simply by looking at a different part of the electromagnetic spectrum. So we shifted from 3 microns to 6 microns, where there's which is a little bit further into the infrared. And at 6 microns, the water molecule has a unique signature due to the bending of 2 hydrogen atoms around an oxygen atom, like this little water molecule here is doing. Hydroxyl doesn't move like this, and so does not confuse the 6 micron signature of water. To search for water on the sunlit surface of the moon at 6 microns, I use the Stratospheric Observatory for Infrared Astronomy, SOFIA. SOFIA is unique because it's a telescope on an airborne Boeing 747 flying at 45,000 feet. This is an illustration of what SOFIA looks like while it's flying. You can see that there's a cutout in the side of the plane that opens up to reveal the telescope. So with SOFIA, we looked at the Clavius, let me go back. So with SOFIA, we looked at the Clavius crater at high southern latitudes, indicated by the white circle on the moon. With SOFIA, we were able to detect the water signature at 6 microns, making it the first time that water itself was detected on a sunlit surface of the moon. This answered the decade-long question of, can water survive outside of these permanently shadowed regions? This image on the bottom is an oblique view of the Clavius crater where we found the water. The amount of water that we found, however, is quite low compared to Earth standards. For comparison, the Sahara Desert contains 100 times more water than what we detected at the Clavius crater. So we won't be going swimming on the moon anytime soon. So now you may be wondering, well, how did all this hydrogen and water get to the moon in the first place? Well, there's a few ways. One way is when the moon was first formed and before it formed a solid surface, comets carrying water impacted the moon and left behind water inside the lunar interior. This internal water would later be erupted onto the surface of the moon through volcanic events or dredged up during a large impact that created some of the craters we see today. Another way is that solar wind that constantly bombards the moon. The solar wind is a stream of charged particles released from the sun and is mainly made up of hydrogen. When this hydrogen hits the moon, it reacts with oxygen and lunar materials or lunar minerals and forms hydroxyl and possibly water. And another major way water can get to the moon is through recent micrometeorite impacts. Micrometeorites, like comets, can carry water to the moon or produce the water during an impact. So now we have the history of lunar water, and we know how it got to the moon. So the next questions are, where is the water? How is it stored? And how can we extract it and use it to support astronauts and human exploration? Well, we already know that water is trapped inside these permanently shadowed regions at the lunar poles that are super cold because they never receive any sunlight. At places like this, water is trapped as frost, like you might see on your grass on a cold winter morning, or it could be on little grains of ice mixed into the lunar soil, or it could be a large deposit like an ice sheet. Water ice within these cold, dark places at the lunar poles could be in abundances of tens to hundreds of million tons. But however much water ice is there, the ice is not pure, and so it would need to be refined after being extracted. To extract ice from these permanently shadowed regions, it requires a lot of preparation. The first challenge to extracting water from these regions is the fact that these places are really cold and dark. For example, these regions typically sit around a temperature of negative 390 degrees Fahrenheit. The coldest place on Earth is in Antarctica, but there it only gets down to negative 130 degrees Fahrenheit. Power is another big issue. For space exploration, power is typically generated from solar panels. But when working inside a permanently shadowed region, there's no light available for the solar panels. Batteries are not very useful in extremely cold temperatures and would need to be rechargeable. So to power all the instruments and life support systems for astronauts, we need a reliable power source. Some ideas for this are to have solar panels on towers that can extend high enough to reach the sunlight. Nuclear power is another one, or regenerative fuel cells. Once we get the power inside these regions, we next need to figure out how to extract the ice. There are a couple companies and groups looking into how to extract water ice from permanently shadowed regions. Here I'm only going to talk about 3 potential ways. One way is to heat the lunar soil containing the ice. In this method, the lunar soil is heated to temperatures that are high enough to vaporize the ice. The water vapor is then collected, refrozen, and transported out of these permanently shadowed regions. This method, however, requires a lot of power to heat the lunar soil. Another way is to excavate a large amount of lunar soil and transport it out of the permanently shadowed region to be processed. This is not very efficient, though, as you are hauling out thousands of tons of lunar soil that is not wanted just to extract the ice. And the third potential way is to sort the ice grains from the lunar soils. This method would be similar to how gold miners separate gold from other materials. The ice grains in these regions are as hard as granite, and therefore they can be separated from other grains. This method does not require changing the water ice to a vapor phase and back to ice, and it doesn't require hauling out tons of excess materials. Once the ice is extracted, though, it is taken to a chemical processor that vaporizes the ice, purifies it, and then it can either be converted to oxygen, rocket fuel, or water for the astronauts. So since we did find that water can survive on the sunlit portion of the moon, we may be able to extract water from a less complicated location. The water we detected with SOFIA at the Clavius crater could either be attached to lunar grains or stored within impact glasses. Extraction of water from these 2 water locations requires heating the lunar soils or glasses. If the water is just attached to a lunar grain, then we only need to heat the soil enough to break the bond and capture the water. If, however, the water is stored inside these impact glasses, extraction requires high enough temperatures to melt the glass and release the water. Extraction of this water is less complicated than that of water ice in the permanently shadowed regions. There is a catch, though. The amount of water from the water attached to lunar grains or stored within impact glasses is much, much smaller than the amount of water ice in permanently shadowed regions. So this method may not yield a lot of water and therefore may not be feasible. There are some locations, however, outside of these permanently shadowed regions that could potentially concentrate water. These are the volcanic deposits that contain the glass beads. The beads may store water from the lunar interior and could be melted to extract water if the abundances are high enough. Another possible route that doesn't include mining water, but instead producing water from the moon and the lunar soil. Most of the lunar soil is made up of minerals that contain oxygen. One mineral of particular interest is ilmenite, which is made up of iron, titanium, and oxygen. Experiments using ilmenite in Apollo samples have shown that water can be produced by heating the sample and adding in hydrogen. So basically what happens to the sample when it is heated and hydrogen is added, the ilmenite breaks up into free iron, titanium dioxide, and most importantly, water. But a byproduct of this reduction of ilmenite is the release of iron. Iron is also a resource on the moon that could be used for building materials. This process, while promising, has only been done on a small scale, but the European Space Agency is already planning to test this on the lunar surface with the Ross Cosmos lander in 2023. One of my colleagues, Hannah Sargent from the UK, is actually working on this. So in order for this process to work though, there needs to be a lot of ilmenite. And the best place for that is on the mare, which are the dark patches we see on the moon. Now let's come back to Artemis and how we are preparing to send humans and back to the moon. I already talked a little bit about the work I do with SOFIA, but how does my work on lunar water help us prepare for the Artemis program? Basically, I am an observational lunar scientist. I use 2 Earth-based telescopes, the Stratospheric Observatory for Infrared Astronomy, SOFIA, and the NASA Infrared Telescope, IRTF, in Hawaii. With these 2 telescopes, I'm trying to understand and characterize the behavior of water, its abundance, and its distribution across the moon. By understanding how water may be moving around the surface of the moon, we can determine the source of water and the retention of it. By looking at the distribution of water across the moon, we can estimate its abundances. We can look for places that could be concentrating water, that could be potential landing sites for Artemis in the future. So this is a very exciting time for lunar science and exploration. The moon is a spectacular sight and something that all humans on Earth have in common. Thank you all so much for allowing me to talk today. I hope you enjoyed learning about water on the moon and the Artemis program.
All right, well, thank you so much. This is really great. There were some really interesting things that I had never heard before, and so that's fantastic. And we have some really great questions here too, and so let's get right to these. So a while ago, Darian and
Just a minute. Can anybody hear me?
Yes.
Yes.
We are an hour and a half into this program. Do you want to listen to the next 15 minutes of Q&A, or you're welcome to step off if you like. As we mentioned, my friend Denny out there in Arizona, there is a lunar eclipse in the morning before dawn, if the clouds aren't here. As I speak, though, I can see the sun going down, so maybe that's hopeful. It starts about 4:45, and the moon will be in the southwest as it sets just before sunset. I've forgotten the time. I did put the numbers on the email. Probably need binoculars to see the last part of it. And also this week, Venus and Mercury are really close together, and that will continue next week. They're within a half a degree on the evening of the 28th. So they're a little bit north of west. And of course, you can always see Venus, and Mercury is getting a little dim because it's coming around toward inferior conjunction. So it's a little skinny crescent. But that might be something interesting to look at. So what's your vote one way or the other, to stay on or call it an evening?
I need to go.
I think I'm going to call it an evening.
Me too.
Anybody else want me to?
But speaking of Mercury, the last members night, we got to see Mercury.
Good.
It was up pretty high.
All right. Well, I'll put the URL back up if you want to look at it. It's just a Q&A talking about possibilities of finding water on the moon. But the first phase of the Artemis, I believe it starts next year with the lunar orbits. So we're moving forward to going back to the moon. I thought we would be well established there by now, but at least we're making a move that way. So we might be up there with our Chinese friends. They're really working on that too. All right, Richie, good to see you on.
Thank you, John.
All right.
There's
Thank you.
meeting
And
this
thank you for
Saturday.
hosting this.
Sorry, we didn't hear that.
Is there
Thank you for
still,
hosting this.
is there still a meeting this Saturday?
It's a little doubtful. I gave the people till noon tomorrow to make reservations. I haven't heard from too many, but I will send out an email tomorrow, David, okay?
Okay,
For those of you who don't know, we were going to try to have a guest night by invitation only on Saturday. And David and some others had volunteered. I would say it's probably only a 10% chance of having that go from the weather forecast. We'll just have to see how it goes.
John, I joined the club while we were doing you were doing the presentation. So I'm your newest member.
And you're probably our second most distant member.
Yeah.
All right.
My daughter in the Bay Area is also a member.
Oh, okay. Hi, Richie. Yeah. It's been 10 years since I moved.
Oh my. Well, Marilyn and I have been talking about places to go since we couldn't go to Canada for our 50th. So maybe we'll head out your way sometime. See you and Barbara and all your dogs.
You're all welcome to come.
Yeah.
We got a blue sky right now. About 90% of the time.
Take a picture so we remember what it looks like.
Okay.
All right. Thank you all for joining us. Go
Thank
get
you.
your snack. Enjoy the evening.
Thank you.
Good
Bye.
night.
Night.
Good night.